Good morning. Before we get back to contact problems, I wanted to make a couple of comments about the last test. The first is technical. This problem HI, considered a crank on a bicycle wheel. This is actually the dimensions of my bicycle. And this would be the situation when I boarded the bike. I put all my weight on one foot. I don't weigh 200 pounds, but there'll be a certain dynamic enhancement as you swing your leg over and get on the seat. So this is not an unrealistic load. And what I want to show you is that what the maximum shear stresses are. The maximum shear stresses occur at A. There's a little fillet radius as this thing goes into its shaft. It's in a sleeve. This is point A. And if you're looking down at A, what you have is a uniaxial stress state, sigma B. So if you look at a 45-degree element, this is tilted by 45 degrees, then what you'll have is the stress state has become biaxial in terms of normal stresses. But some of this stress has been converted into shear. And this is this tau max equals sigma B upon 2. Now there is a distribution of the shear stress through this section, and its maximum is at B. If I cut through that section, that shear stress distribution looks like this. It goes to 0 on the outside. So when it's lined up in this direction, it is 0. You have to get on 45 degrees to get a shear stress. So this is not an accident. It goes to 0. But here's its maximum at B. And that for a circular cross section at B is 4V upon 3A, where V is the shear force. That would just be, or if you like, so V is just 200 pounds. And D was 1/16. Oh, there's a 3 here. 1/116. If you calculate this, this is 0.3 KSI. And the answer we had for this, essentially 3 KSI. So this is the maximum shear by a factor of 10, okay? Now that would always be the case, it's often the case, but even if I did the following, even if I stepped on this thing here, okay? Well, my shoe is about 2 inches. It'll probably wrap around here a bit. So maybe a 1.5 inches of contact. And so the force would move in here, and the moment arm would just be 3/4 of an inch if you stepped on it. Now, I'm not encouraging anybody to do that. That doesn't seem like a very sensible thing to do. But even if you did that, that would reduce the tau max. Would go down. It used to be 3 KSI, the tau max at A. And it would go down because the moment arm has gone down. The moment arm used to be 3.5 inches, and now it's 3/4 of an inch. Let me write that. Let me make this quarters, and this 3.5, let me make it halves. So it goes down by 3/14. That's still 0.6. And the answer I had here was 0.3, so it's still 2 times. So what I'm trying to tell you is the books give a lot of attention to the shear stress due to the shear force. Okay? There's quite a bit written in books about it. And it's all correct, okay? At least as far as I can tell. The thing is that those stresses, first of all, they're at a different location. I've seen practicing engineers occasionally try to add the two. That's wrong. One's at the center of the shaft and the other one's the outside of the shaft, okay? And typically it's smaller. Even in this circumstance, it's a factor of 2. If somebody asks you for the maximum shear, let's go get the bending stress and divide by 2. Are there any questions on that? Let me make a couple of comments about the test. All right. I was pleased to see a number of you did well. That's good. I would be pleased to see all of you do well. But it's important that if you don't understand this material that well, that we don't let's let you go on. Now, my impression from our kids that went to high school is that if you worked hard in high school, you got good grades, and if you didn't do too much, they let you pass anyway. Well, that's not good in engineering. Okay? What's going to happen in engineering is that the standard of engineering is going to keep going up. It's gone up continuously since I've been in this country. When I first started consulting, it was not unusual to go to a plant and the lead engineer wouldn't have an engineering degree. That's getting less and less common. And as technology changes, and it's going to happen, the oil and gas industry is going to be with us for a long time, but at a diminished rate, and people are going to have to develop new technologies, then we need engineers more and more. And that means we need people who understand the stuff. So you need to understand the stuff reasonably well to get through this class. That said, that if you're trying quite hard and you're not doing well, don't get down on yourself. Your background may have been weak in high school or something like that. And if you put a real effort into this class and solve problems, then when you take it again, you'll get a new set of problems. And with problem solving, your understanding goes up and you'll eventually develop and be good, okay, with a decent level of understanding. And MECI at LSU does have a good reputation. I mean, we are a premium department, meaning one of between 6 and 12 universities in the country that some major companies recruit from in regards premium, okay? And we have good starting salaries, and that's because our MECIs have a good reputation. And that'll only continue to be the case if we produce people who understand stuff. You know, I had beers with the engineers on Fridays, and you just need to have one guy walk in and say, look, we just hired a guy from such and such university, and we gave him this clamp, and he couldn't even draw the free body diagram. And all that needs to happen is another guy said, well, we got somebody from that. And Bill said he didn't know what he was doing either. And boom, the reputation started to get shattered. You know, reputation building is like forking up a snow-covered mountain in bare feet. That's not easy, okay? Reputation loss is like going down the other side on a slide. It's relatively rapid. And so we need to graduate people who understand stuff. Now, I'm here to help you try and understand stuff, and you're welcome to try me in office hours. And I had a comment from a student to try and give you more opportunities to solve problems, and I'll try and find more problems. Sometimes that's not trivial. Some of the stuff we've done on convergence checks is relatively recent, and there aren't books with problems there to the best of my knowledge. But I'll try and find that a bit more. And I'll make the following thing. If you email me before class and you want to see me right after class, I'll be here in the office. You want to see me in person, you've got something you don't understand, just send me an email. Okay? If I don't get any emails, I'm not going to stick around. I'll go to the gym. But if I do, I'll give you a hand. So I want you to understand this stuff. And I'd like nothing better than you all to understand and do well. Now, if you're not working, I really don't care. That's your choice. But if you're putting an effort in, I'll try hard to help you get to the right level. And if nothing else, if you get a D in this class or a high F, then you'll set yourself up for doing better the next time you take it. Okay. All right. That said, I think Dr. Wahab felt that we had to keep all the tests for ABET. That's a little bit of an overstatement. We have to keep 3. So if you still want to get a copy of your test, or if you wanted to keep the copy that you had, then Mohammed will be available after 3 today to give you an opportunity to get the test. And if you email him, he'll at least scan the first page and send that to you so you can see how you did on each part. In terms of preparing for the next test, one of the things you well advised to do is to go through the work solutions that have been posted and make sure you understand it. If your work solution is about twice as long, then the one that's been presented is more effective. Now, I'm not saying there aren't other effective solutions, the ones that were posted, okay? And if they're about the same length, that's fine, okay? So, but if they start to be twice as long, or if you didn't get there, then you want to look at that and understand that, because that stuff implicitly will be in the next test, because the next test tends to build on. Well, with that said, are there any questions on that? Okay, let me recap this roller contact. Not the greatest of circles, but still. Lots of books press these things together with P, a compressive force, which for rollers is FORL. And L is the length out of plane. While books use this, I'm not going to use this P because it's a little bit hard for you to tell the difference between my uppercase P and lowercase p, which is the pressure. So I'll just use F upon L. Okay. When you push these two together, you get a contact extent, and the traditional letter for that is 2A. 2A is the total contact extent. So if somebody asks you what the contact extent, it's not A, it's 2A. Okay. But we have a formula for A from Hertz. If you do what we did, a little bit of dimensional analysis, it has to be the square root. So this formula looks slightly neater if you put P in here, but for the reasons I just explained, I'm not going to do that. R is this radius, and it's a collective radius. And one of the things that can happen here is if R2 was a slab, then it would be infinity and nothing would happen. R would just be R1. If R2 equals R1, it'll be 2 upon R1. When you take reciprocal, you get half the radius. And this radius promotes A. as a square root, in fact. And so when you do this, you're moving material from it, and you're making contact grow less rapidly as you push them together. The converse is if this thing curves up like this, then R2 becomes negative, and you're promoting contact. So you have to worry about the signs of these things. Physically, they're dimension, no question. But when you use them in this formula, they have signs. When they're curved away from the contact area, they're positive. When one of them is curved this way and the other one's curved the other way, one's got a plus sign and one's got a minus sign. E is a combined E. If this thing has a Young's modulus E1 and U1, whereas this is E2 and U2, you don't get straight E in here. You'd expect the stiffer it is, that's going to resist the growth of the contact regions. That's why E's on the bottom. But as you push down on it, it pushes out, and that stuff pushes back. There's a Poisson's ratio effect. And so this E looks like this.
That's E star, right?
Yes, thank you. So if E2 was infinite, what's that mean in engineering? A factor of 10 or maybe 100 times bigger. You throw this away, you flip this over, you get E1 over 1 minus nu1 squared. When you divide by 1 minus nu1 squared, you make it slightly stiffer. That's because of the Poisson's ratio effect of pushing it around. If E1 equals E2, you'd just get a 2. And so this modulus would become E1 over 2 times 1 minus nu1 squared. That's very common. You often push things with the same modulus here. And so now, because they're both compliant, the effect of E has gone down. Then the pressure,
just to be clear, that L is the length
yeah, out of plane.
out of plane. All right, thank you.
Yeah, let me clarify that. So let's suppose this was bigger than this, then L is the net length that's in contact. Okay? So per unit out of plane length. So you get this distribution that goes to 0 at x equals plus a and minus a. X is the dimension across the contact region.
Dr. Sinclair,
Yes, sir.
what's the difference between the L and the 2A?
2a is in this plane. So, okay, yeah, this contact region looks like this. If I look down on the contact region, it'll be 2a this way and L this way, out of plane.
Okay, I see.
Now, sometimes when you're doing these contact problems, they'll just tell you this P, this force upon length, okay? And that's why a lot of the formulas you have P, and the only reason I put F upon L, it's just going to be your P. I'm telling you this, you just replace this by P, but I did it because with my handwriting, it's not going to be that obvious what P I'm talking about. But that's the only reason. But books commonly use that. Okay. Any other questions? Okay. So then P naught is 4 upon pi times the average value. So if you divide it by the average pressure, this is a stress concentration factor of 1.27, which is modest. Okay. And you can work this out. You can get P bar is 4. And the area is 2A times L. That's a 2. And when you're working these problems, oftentimes you work out the contact region. So this is a common way of working them. Then you just use this formula, okay? But you can combine these two, and I did that. You substitute for A, and you get the following. And if somebody just asks you what the maximum contact stress is, you could just go straight to this formula if you like. Okay. Oftentimes you want to know what the contact extent is too. One of the reasons you want to do that is this thing expands, and oftentimes it's small, but there might be some feature, there might be a groove or something like that. You want to make darn sure it doesn't hit the groove. So it's quite often you want to know this. But if you just want this, you can just compute it with this formula. Having computed A here, you can compute it with this formula. Either is fine. What this teaches, though, is that P naught is proportional to the square root of F. So in just about all your other stress analysis, when you double F, you double the stress. That's not the case here. When you double F, you increase the stress by 41%. And why is that? That's because as you increase F, it's P here, that increases the stress, but you spread it out over a bigger area, and that reduces the stress. So the combined effect is you still increase the stress, but not as rapidly. Then there's one other slightly. Yes, sir.
Question about one of those formulas.
Sorry.
The P equals P naught over the square root. It's 1 minus what? What is that over A?
Sorry, which formula are you talking about?
P equals P naught square root 1 minus something over A squared. What is that?
Oh, that's X.
What is that X dimension
Oh,
refer to?
okay. That's the lateral. That's X there, okay? That's a fair question. And so as you go across the contact region, the stress looks like this. When you get to the edges, X equals A, this will be 0. It has a peak value here in the middle of P naught, okay?
Move up the paper.
That's true of nearly all contact problems. They go down like the square root at the edges. So this stuff's a little counterintuitive compared to what you've had until you live with it for a while. But it's important in key because a lot of failures occur with contact stresses. And one of the things that guides failures, you're normally talking about metals. And metals, we're going to talk about this more later on, but they fatigue when they start to yield. And that's driven by shear stress, not normal stress. And so tau max is only 30% of P naught. And that's because the stresses right under the indenter are all around compressive. And so when you start to take the differences between the two and divide by 2, you don't get much. But what happens is this thing occurs. It occurs in both of them, but this is 2A. It's pretty close to here. This distance here is 3/4 of A. Okay. It's going to turn out most of these metals, we'll do some examples. I think I did one last time, that this A is in thousandths of inch. So 3/4 of an A is not very far below the surface, but it's subsurface. And one of the things that means is damage occurs below the surface and you don't see it until the piece pops out and the thing is already damaged. That's the standard failure. But for yielding, tau max is SY upon 2. When you have a uniaxial tensile test and you pull it, and you get sigma X or sigma Y, shall we say, equal to SY, then the peak shear stress is half of that. And so yielding is occurring when the tau max is SY upon 2. Okay. So if you, this and then implies the tau max is 3/10 P naught equals SY upon 2 at yield. So P naught 2 goes into 10 5 times. It's not twice as big as the yield strength, but it's getting up there, 1 2/3 time. And so this means when you design things, you can have stresses that exceed the yield strength and not have fatigue problems. It's okay. Moreover, if you're below it, because these contact stresses depend upon the square root of F, okay, then you can actually increase your load quite a bit before you get yielded. And so this is all a little bit counterintuitive. One of the reasons for studying. Let's see how this. Are there any questions? Any other questions on this? I appreciate your questions.
So this gets applied for cams and cam followers, I assume.
Sorry, what was that?
This concept gets applied for cams, I assume.
Well, cams would be like a roller. Yes, I mean they have a bigger radius on one end and a small radius on the other end, and so when that makes contact, that'll be a rolling contact. Roller bearings and cams would be a common application. Gears, another common application of this sort of thing. Okay, so those are very common. But yes, you get it in cams. Any other questions? All right, well, let's extend this. It's going to be similar physics, but not identical. Let's talk about contact of spheres. Let me draw a better circle here. Now, these are no longer cross sections of rollers. And this force, we'll just call it F. F is the compressive force. There's no longer any out of plane length. Okay, these are circular things. And so what's going to happen here is you're going to get a contact region in here, and that contact region will look like a circle itself. We'll continue to use A as extent, but A is now the radius. Before, the contact region was a rectangle for rollers. Its length out of the plane was L and its width was 2A. Now it's just a circle. So you may be able to see this. Demonstrations on this system leave a bit to be desired, but these are two fairly curly looking tennis balls. Okay. And so if they're fuzzy, like they need a good shave, right? And I push them together, and I think you'll be able to see that's a flat line, a straight line, and that's a circle. Okay, that's what's happening as I push these two together. So you would expect that the contact radius would be proportional to how hard I press. And you'd have to take my word for it that I'm pushing harder when I, but you can try that yourself. Okay, and you'll see that, and these things are nice and deformable, so you can actually see the contact region grow. As I said, these are slightly fuzzy, If you had newer tennis balls, you might see it more easily, but it's a straight line across there. If this is the radius, then if you make this a bigger radius, you'd think you would grow the contact region. There's a partial demonstration of that. Now here, I'm going to push about the same, okay, ballpark, not precisely, but ballpark. There's a fuzzy contact region before I even start to push. But even so, when I push, I'm looking at this sideline, I'm looking down on the top. It looks to me like the contact diameter, 3/4 of an inch. Okay. Here's 2 golf balls. One of these I quite like. It's actually played 9 holes with me and it's still with me. But if I push these 2 just as hard, you can see it's a much smaller contact. It looks to me like maybe an 1/8 of an inch. Okay. So as you make the radius bigger, you get bigger contact. The other thing that's happening here is these golf balls are a lot stiffer. So as you make them stiffer, you're going to reduce the contact region.
So can you show where that 1/8 came from? Like, can you,
Sorry?
like
So-
the 1/8 on the golf balls, can you show where that came from? Like, was it from up and down?
The one upon E?
The 1/8.
Oh,
One,
yeah. It's very hard for you to see, okay? Okay, so, but I'm looking at the contact region right down here, okay? And when I, so it's hard, at least I don't have the skill set to show this clearly on this medium. But when I push this together, you can see there's quite a big area, okay? That looks like maybe 3/4 of an inch. If you look for the same contact region here, now it's hard to see it down low. But maybe you think it's 1/4 of an inch. I don't think so. But it's this length in here. Okay,
sounds good. Thank you.
it's much more. Okay, but with these demos, you can do these yourself at home and see the effects. If I'm not showing them that clearly on the computer. Okay, if you get 2 tennis balls and push them together, you get a much bigger contact region if you push together 2 golf balls with the same force. Okay, but one of the reasons for that is that these things are a lot stiffer. They're a lot stiffer. If you push these, if I push this, I can make it give all the way. If I push the golf ball, my finger gives, but nothing else gives. Okay, and so this has got a much higher modulus in effect. So what we expect out of all this then is that A is proportional to F R upon E. And if we do the units, well, units of force are F, units of radius is length, units of E are force, the units of stress over length squared. Divide by 1 upon length squared, you get length cubed. So what we suspect then from this simple analysis is A is proportional to the cubed root of FL upon E. So it increases with force F, but not as rapidly as the roller contact. And that's because the outer plane direction is behaving differently. Okay. Well, there is a solution to this done by Hurt. Is there any question on that?
That's a cube root, right?
That's a cube root, yes. If you're more comfortable in terms of analysis, you can write it like this. Okay. So this is a cube root because A is a length And from the units, we got this quotient was L cubed. So to get a length, we have to take the cube root.
Now, is A proportional to that cube root or equal to that cube root?
Proportional. We don't know what
Okay.
the constant proportionality is. We'd have to
Okay.
solve the problem, okay? And we didn't solve it. This is just a simple little piece of dimensional analysis, is what it is. And these things here are sort of common sense, okay? And then you get this grouping, and you could call this dimensional analysis or units, whichever you're most comfortable with, and that tells you this, okay? But we don't know we'd have to solve the problem precisely. Now that is not trivial. I think I mentioned last time you have to solve an integral equation, but it's been done by Hertz, and here's the solution. But it will look like this. It will not deviate from the common sense. So here's the Hertz solution. Let me get rid of some of these balls.
Quick question, Dr. Sinclair. Did you mean to write L
Sorry?
in those last two equations? Did you mean to write L, or are those supposed to be R for the radius?
Oh, sorry. Yes, thank you. It has the units of L, but yes, it's R for the radius. Thank you. Yes. Yes. Yes, that's right. So here's the formula. Well, in general, these will not be equal. It might be better if I'd chosen the bigger difference between the two. Well, here we go. For the tennis balls, these radii were equal, and so the golf balls, but they don't have to be in general. And they will not necessarily be the same material, although that'll often be the case. And this force F, which is just a straight force, then A, according to the Hertz solution, I'll use this cube root, but you're welcome to use the 1/3 power. And now we have a constant proportionality. It's the cube root of 3/4. The cube root of 3/4 is about 0.9, so it's very nearly a constant proportionality of 1, but it's not. And again, the way you get these radii is you add the reciprocals, then take the reciprocal of what you got. And again, if the R1 and R2 are like this, then this thing, when you add these two, this gets bigger. When you take the reciprocal, it gets smaller. So AO gets smaller because this thing is curved away from this and not promoting. On the other hand, if they're both the same way, one of them will have a minus sign. And when you curve it around like this, you are promoting A. And so what this will be plus, minus, so this gets smaller. So reciprocal gets bigger, so A gets bigger. And then this E star is the same as before. And we can go and get contact pressure. This is the little circle 2A. Okay. What this contact pressure looks like is it very similar to the one we had before. It rises like a little hat. So if R is the radial distance out from the center of contact, then the contact pressure looks like so what that tells you is whenever R equals A, it goes to 0, and P naught is the max. And if you do the integration, then you can get the average, and you'll find when you integrate this, that the average, of course, will be somewhat less than this value. In fact, it's 2/3.
Should that be R squared over A squared?
Sorry, yes, my mistake. Sorry. Thank you. Yes, what I just inadvertently wrote down is for the pressure of a flat punch. Sorry. Thank you. Okay. Yes, it goes to 0. It would have gone to 0. Yes. All right. That's just a stupid mistake. Okay. This is the max pressure. P bar here is F upon pi A squared is the average pressure. The same thing happens here. We're going to be dealing largely with metals, so we're going to be concerned about, oh, what we could do, obviously, if you divide P naught by P bar, it's 1.5. For Walter contact, it used to be 1.27. So it's a slightly higher stress concentration. But these are not terribly big. You've met bigger stress concentration factors than this in your charts and stuff like that. 3 is not an uncommon number. What makes these stresses so big is that this A is small. So these average stresses can be quite high, but they will get enhanced. Okay. And we're going to be dealing with metals and fatigue, and so we're going to want to know what the shear stress is. Well, these are not necessarily the same radii, but they have a contact extent of 2A. Then the maximum shear stress again in round figures is 30% of P naught. These numbers, I've given you 30% for both of these. They depend a little bit on some Poisson's ratio effect, but the first order this corrects the thing. And it's fairly close. It's A upon 2. So this is the contact region. This is 2A. And this depth here is like this, A upon 2. So it's near the surface. A is small, so A upon 2 is even smaller. And that's where the maximum shear occurs. That's where yielding is going to occur. I can rearrange these to give you some sense of how this P naught behaves by substituting for A. what we had was that P naught was 3 upon 2 P bar. And A was the cube root get the numbers 3 F R upon 4 E star. So then the P naught, when I combine it, is 3 upon 2 F upon pi 3. This is A squared, so it's going to be 4 I squared it, and then I'll take the cube root. I want to put this under the cube root and simplify all this. There's no pi in there, so I'll leave the pi outside. So it's going to be 3 cubed, if I put it under the cube root. F cubed, 2 cubed. And I squared this before I took the cube root, so that, and it's reciprocal. So 4 squared let's concentrate on the symbols first. We'll get the coefficient in a minute. That's F cubed, F squared, so it's just F.
Can you scoot it up a bit?
Oh, sorry.
Thank you.
E star squared, there's no other E star, so it's just E star squared. And down the bottom, there's R squared. And there's some sort of numerical coefficient. Well, let's see. 3 squared, 3 cubed, that's just 3. 4 squared is 16, 2 cubed is 8, so that's 2, so the coefficient is 6. If you're going to use this form, you've got to get that numerical value correct. As I said with the cylinder stuff, you can often just calculate A, then go use this formula to get P naught. But what does this teach us? It teaches that P naught is proportional to F to the 1/3. Okay. So if you double F, the cube root of that is 1.26, you get a 26% increase in P naught. So it's slower. For these spheres, it's slower. That's because the contact region spreads in 2 directions. And so that's mitigated. When you doubled F for roller contact, it could only spread laterally, not the outer plane direction stayed fixed. And so that mitigated it, and it meant that the maximum contact stress went up as the square root of F. But here, it can spread in both directions, and so you get the cube root here. On the other hand, for R squared, it's R to the 2/3. So if you double R, which is what's often used to try and mitigate these stresses, you try and increase the radius. Some of these radii are local. Then you actually get this going down by R to the 2/3 goes down by 37%. And in fatigue problems, dropping things by 33% or so, 37%, it can be quite significant. Okay, it can really be quite significant. Are there any questions on that? It's very parallel physics for the cylinder case. Okay, what you've got that's new here is you have changing contact regions, changing regions where stresses are applied, and as a result, you have significant changes to the way the stresses depend upon the force. not just linear. Most of the time it's just linear. Let me start an example of this. Now you can find, I went and looked, and you can find an example of these contact problems in the book, Scheduled Problem. I've only checked the 5th edition, but I suspect this is in the 7th edition. Which you should be able to do. But then we do a contact, or set up a contact problem for a ball bearing. So here's a little ball bearing. These ball bearings have spaces here which holds the balls apart. It keeps them separated. Okay? And let's see, maybe I can mark it here. If I turn the inside radius, then just as previously, it travels a lot further than the little ball here. This has, actually looks like about half here. Okay. It has about half the velocity, but it's got a slightly bigger radius. And I think that roller bearing I had a lot more slipping. This thing doesn't seem to be slipping at all. And so when I turn this, let me get my hands out of the way. I can see the mark quite clearly, but you can't. It's come down to the bottom. This is almost at 9 o'clock now. And that's about what you'd expect. With that roller bearing, it wasn't moving as far as that because there was more slipping. I could see there was more slipping. Without slipping, its velocity would be half, and it's got a slightly bigger radius, so it doesn't quite get to 9 o'clock when you get to 6 o'clock. And this is one of the reasons why these stresses are important, is because this thing here has seen several of these balls as it went around, and so it's seen their stress go off and on, and so is the outer radius. Okay, and for that matter, the balls themselves are spinning, and so they see contact stresses on either side, and they switch off and on. So this is a real candidate for fatigue. And so one of the reasons you want to try and analyze the stresses of something like this is you want to make sure that the yield stresses are not close to, the shear stress is not close to yield, and that'll help you avoid fatigue. Okay? There are some other rules. What's going to happen in practice is this bearing will have some rated value, and you can sort of do catalog engineering. You can do that until you get something that fails, in which case you need to kind of understand what the heck went wrong. Okay? But oftentimes you'll just get the bearing. Well, when you're picking bearings, oftentimes in practice you'll do reverse engineering. Somebody has already picked that bearing, and if there's no reports of any problems, you just pick the same bearing. But then when you start doing something new, then you can get sort of load capabilities of bearings from tables. But every so often something weird happens, and you need to start understanding what's going on with these. And so we'll do one of these problems. So I'll come back and analyze the stresses on this little roller bearing under a nominal load and see what they look like. And again, what's going to happen? This is steel. I suspect that this is a relatively high strength steel. I don't know what it is. It's some years since I got this thing. But it's an MRC bearing. But the stresses will be under moderate loads reasonably high. Why is that? It's because the contact areas are small. On the other hand, what's forgiving is the shear stresses are not that high. And so as a result, you can live with it without fatigue. So we'll do an example like this. But are there any questions now? We're going to take a break. Okay, let's take a break for 5 minutes, and then we'll solve for the stresses in this roller bearing. No, sorry, ball bearing. Okay, let me start to do with this. The outer, right, I drew this around the outside because that's what I could draw, but I'm really trying to get this diameter of this inside diameter of the outer ring. And if I measure that, I get just under, it's a little bit tricky because there's a little slot in here. I'd say this is about then we've got a inner. This is again not drawn to scale, but that's where this thing is here. And again, it's a little bit tricky. There's a little slot in here, and so you can measure this, but it's a little bit less. It's a little bit less than that. I'd say it's about 1.5 inches. Then between these two, these are the inner radii, inner part of the outer ring, and this is the outer part. And so these boards actually go somewhat inside. And they're spaced out. And again, they're not completely trivial to measure because there's a casing around them. I estimate them to be about 3/16. So this means let's call this R1, be 3/32. And R2 here will be half of 1 7/8, be 15/16. Okay.
Could you
But
move the paper up, please?
Sorry, it'll be half of 1 7/8. That's 15/8. Half of that's 15/16. But here, it's the same direction as R1, and so it's increasing it, so it's got a minus. On the other hand, on the inside, it's going to be half of 1.5, which is 3/4, and it's positive. So the key stresses are going to occur at the inner radii, the biggest stresses. This is what we're going to concentrate on. This is steel. (30 times 10⁶ PSI is a common value taken for steel. Steel vary a little bit, probably between 28 and 30. This is standard sort of value. If you want to get standard values for any material, you can go to the appendix in the back of your book, and those are accepted values. Okay. You would only change them if somebody had done some testing at your workplace and had a specific value. And a common value for the Poisson's ratio taken for steel is 0.3. And again, this varies some too. On the other hand, typically these variations don't make a lot of difference. Now I'm going to say the average force here, I've lost whatever catalog I had that described this. I don't know, I would say F is about 6 pounds.
What are those subscripts on those R's?
R1, hopefully that's clear. R1 is for the ball itself. R2 was for this this radius or this radius. Okay. And I'm going to say a ballpark figure of 6 pound force. I got that by looking at this thing and thinking the sum of the forces will be around 10 pounds. Where did that come from? You get 6 pounds from this. These two are well away from that, not like the roller bearing, they're not close. So they might only be a couple of pounds each. And these two will be basically zero. So that would give you about 10 pounds. And that would not be an unreasonable lateral load for a bearing like this. I'm not saying it is the rating, I don't have that, but that would not be an unreasonable number. So what we're going to try and do here is find sigma max and tau max. As I said, the max is at the inner race, so we need to go and get R. It'll have the smaller R. Okay. Let me show you. When they're both positive, the sum will be bigger. So when I take the reciprocal, I get smaller, so I get a smaller contact radius. Contact radius is proportional to R. And so R1 was 3/32 seconds. That's its reciprocal. R2 was 3/4. That's 36 upon 3. That's 12. That's 1/12. Okay. So, sorry, 11. I misspoke. Yeah. Yes, 36 upon 3, 1/12. Okay. R was 3/32 seconds. 1/12 is less than that. 0.083. 3/32 seconds is about 0.1. A little bit less. 0.094. Okay. So what's happened is the radius has gone down because both of these were positive. Sometimes it's a little hard to see that because you're adding it and you think you might be increasing it. Well, no, you've got to take reciprocal. We did this before when this was 30 times 10 to the 6 and u was 0.3. We got 16.5 times 10 to the 6. We got that in example 13. Then we can compute A. F, I said, was 6 pounds. R is 1/12.
So we use the spherical formula even when only one of the objects is spherical?
I'm going to get to that. Okay. Yes, that's very, very good question. Yes, what we have to do, you're completely right. Let me get to that in a little bit, but that's a very good comment. Okay. Okay. And so we're going to use it in this plane, and in this plane, this ring looks a bit like a sphere, but you're quite right. Out of the plane, it's not. So we're going to fix that. Okay. That's exactly what we're going to have to do. Okay. And so if you calculate this, it's 2.83 thou. That's thousandth of an inch. Okay. Or if you'd rather, But back to the last question. Out of the plane, one of the objects is spherical, okay, but the other one is not. So in this plane, if I could take the cover off this thing here, it would be a circle, and this is a circle. So that looks like spherical. When we turn like this, then that's still the ball and the ball bearing, but this other surface looks like this. Okay. Out of the plane. So in that direction, we can actually make an estimate of the contact region just by looking at it. Okay, and so this is one contact. This is going to be bigger. Okay, what will happen here is I'll put this groove in, and this groove is shaped with a very similar radius to promote contact. But they'll design this carefully. So what happens here is there'll be a separation before you get to the where this thing hits the flat part. Otherwise, you get a high stress there. And so there is some dimension here of the contact extent. And so I've looked at this. I put this, got a flashlight and a magnifying glass and tried to look sideways and see what this is. And I estimated that A plus, that this whole length here was about a 16th. So I have A plus as 1/32. Okay. Or if you like, 31 thou, an order of magnitude bigger in that direction. Okay. So that's what you're going to do for these spherical ball bearings. Within one plane, they're both circular, so that's absolutely correct. This other plane, you just estimate the contact region by taking the groove and taking a little bit less than the groove. There are some detailed calculations on how you do this, but by and large, if you get the extent of the groove, you can get it very easily if you can take it apart. This thing doesn't come apart easily. But you can measure it, and then if you take, say, 80% of it, then that'll be that length there. Okay. That was an excellent question. So here's the contact region one. The contact region is an ellipse. And that was 2A. A was 2.83, so it's about 5 thou. That would be 1/16. About 60 thou. Then to get the area of ellipse, the area is pi AB. If A equals B, it would be pi r squared, it would be a circle. So then P bar is F upon pi A plus. Now I'll put in 3 figure numbers. 2.83 for A, 1/32, admittedly an estimate for A plus. So even with just a rating of 10 pounds, you get 20 KSI for the average pressure. And even with the modest stress concentration factor of 1.5, I'll get sigma 32.4. I'm not saying this is A36 steel, but if it was, it'd be quite close to the yield strength.
So where'd you get the ellipse from?
Okay, let me just get Talmax to answer your question. Okay, but it's not that easy to see. Okay, and I'll get to your ellipse question. So this is 9.72. If it was A36 steel, it'd have to be 18, almost doubled. To get it to double, you'd have to increase that by a factor of 8 on your load, ballpark. Okay, so it's a long way from the load to yield for this bit. Okay. Now back to where do I get the ellipse from? It's difficult for you to see. Let me see if I can sketch it better.
Dr. Sinclair,
Yes.
is a good way to think about how these balls roll through or the shape that the balls roll through is similar to like a saddle.
That's fair enough. Yes. I mean, so let me do a couple of sketches with.
Okay.
So here's the sketch I was showing you. I'm just going to do the inner radius, and then here is one of these balls. And a bit of it's out of sight. There. A little bit out of sight, top part. That's a front view. Now let me go and look from this side here. What this looks like is the following. That's the ball. Okay. If you cut through right through the center down here, this is what it would look like. It's sitting in a groove. This groove is the arc of a circle and has a very similar radius to the radius of the ball. And that's what it's sitting in. The same thing happens on the top. I'm just drawing the bottom. Okay. And so what happened here is we got, despite my figures to the contrary, this length here is very small. This is produced by the contact spreading out, okay? And it's small. This is of the order of thousands. This thing here is machined in place beforehand, okay? The contact extent grows very slightly here, but it fits very well. So it has a very rapid growth. You could do 1 upon R1 minus 1 upon R1 plus, okay? And so they're going to be very close. So this is going to have a huge contact region. It more or less fits in here. And engineers design it. So if you look at this thing carefully, it doesn't see contact all the way up to the edge, but probably with good design about 80%. Okay, and so where I got that contact region was, I estimated this width of this slot as best I could, and I took about 80% of it, and that's how I got 1/32nd or 1/16th for the total. It looked to me like a little bit bigger than a 16th this length. I took 1/16th, it's less than that, and 1/32nd for that. And so when you look down on this region, if you look down the region, you have this very narrow contact region here, very narrow. And so my ellipse was not drawn to scale and relatively wide. So this is across the bearing, that's that way, and this is this way, okay, where it fits into the slot. Okay. And that happens in all ball bearings. Okay. All right, well, I'm going to post problem set 4 today, and there'll be some contact problems. Are there any other questions on this? This is tricky, okay? The reason I do spherical bearings after roller bearings is the outer plane stuff is a bit tricky, without a doubt. You could get the precise radius of this and try and solve it, okay? I know from practice that they're going to design it so it's about 80% of the width, and so use that. But you could actually go and do spherical contact again here, okay, and get your R is 1 upon R1 minus 1 upon R1 plus, okay, and see what the contact region was. You could actually do that. But well, I've just done it by measurement here. So doing the calculations for these spherical ball bearings is not that simple. Okay? Now, for the most part, in practice, you're going to get it from the catalog and you're going to have it loading. But occasionally you're going to have a failure which is a bit peculiar, and you're going to want to understand what's going on. Right, we're going to switch topics. Contact problems are important to see because they introduce some new physics. And if you get comfortable with that, and you get comfortable with the idea that you can have pressures in contact that exceed the yield strength and not have yielding. On the other hand, with a lot of these contact problems, the loads are cyclic, and so fatigue is a problem. And relatively light loads produce relatively large stresses because the contact regions are small. So what we've done now is we've finished the stress analysis, which is a significant chunk. We're going to move into deflections next. Or displacements, if you like. And this is in Jebel Marshak chapter 5, okay, both editions. I think the poll may have just died on my thing. So why? It's not that common in mechanical engineering, but sometimes you have deflection design criteria. I mentioned one to you, the design of passenger plane wings is controlled by the deflection because they don't want people looking out the window and seeing the wings flapping around. It will make them unhappy. And so that's actually more stringent than the strength requirements for those wings. And there are some other ones, certain little clips and things can only deflect a certain amount and be effective. But the key thing you need an analysis to analyze I use SI as an abbreviation. You need to analyze static indeterminate configurations of structures. And you have lots of these. Because these static indeterminate configurations offer safety. They also offer improved strength. Those are the principal reasons. For safety, for example, if you think about the wheels the nuts that attach the wheel of your car to the car, well, you have to have 3 to restrain the various resultant forces. Officially, you could have one very big one, but I'm talking about normal side. If you've got a shear force there from the weight of the car. But when you get a lateral force here, you get bending. If you just had 2 and they lined up on the axis of bending, then it would just bend right off. So you have to have them out of plane, okay, or out of alignment, I should say, and so that you can sustain bending. So you have to have 3. I've never seen a car with 3. Okay. Most vehicles have 5, which means they've got 2 extra nuts there. In case you lose one, you're still going to be safe. I think Peugeot may have 4, the French. Okay, well, at least there they've got 1. So you have static indeterminate structures, you put extra stuff in there, so if something breaks, the thing doesn't break. And there's lots of this, okay, where you have something that's statically redundant, so you'll be safe. But here's another situation. Bending stresses are a major source of potential failure. So bending is a significant problem. This is statically determinate. This is pinned ends. And it's easy to analyze. On the other hand, if we build this beam in, the same load at each end, this is the SI, but it's a lot stiffer. So if you're trying to avoid deflections, this will have 1/5 the deflection of this, and it has lower stresses. Why is that? Well, this is something you're trying to do all the time in engineering. This thing is lazy around the ends here. There is no stress at the ends here. The maximum stress is in the middle. This thing here has stresses here, high stress, and another secondary maximum here. So you're exercising, making the whole beam work. That's one thing you want to constantly do in Merkey. You're concerned about weight. You want to keep the weight of structures down because you're moving things. And so you want the things that you're building to have not have lazy or too much of a lazy part. That's one of the reasons why you start looking at hollow shafts with transmitting torque and so on. The center part is lazy. This beam is relaxed over here, not doing squat. That's not the case here. And so you lower the stresses, I think, memory serves me rightly, maybe 33%. Okay. And that's significant in fatigue. So these are the reasons we're going to do statically indeterminate structures. And to do that, you statically indeterminate structures, as the word static determinant says, you cannot just solve them with statics. You have to go look at the deflections, otherwise you can't do them. So we're going to recap some of the deflection stuff, and some of this stuff, especially initially, is going to be old hat for you. At least I think it will be. But fairly quickly, we'll get stuck into problems that you're going to meet in practice, which are not necessarily what you've had in mechanics and materials. So tension, let's start with the simplest possible case. We have a prismatic bar. Prismatic just means it has a constant cross-sectional area. If its initial length is L, then under the action of the load, it'll increase length by delta. Hooke's law gives you what the stress is. The stress is simply F upon A, and Hooke's law relates that to the strain. Okay. E times the strain is what's equal to the stress. And so you can solve this, and you get F equals E A over L times delta. That's your axial stiffness. And of course, you could take reciprocal of this and put it on the other side, and you can get the displacement for a given force. And this is all old hat, I imagine. It may not be in the front of your mind, but something you've seen. These deflections for certain materials are quite appreciable. I used to have a rubber band around here somewhere. So if I pull this rubber band, okay, you can see it there. Okay, if I pull it with just a few pounds, I double the length. So easily. That's because E is of the order of it's got a low Young's modulus, and so it doesn't take too much. This area is pretty small. If I do steel, here are some specs. 1/32 of an inch. That's actually quite a thick wire. I think when I applied this to the rubber, that might have been 10 pounds to double the length. If I apply that and look at delta for steel, it's negligible. The area is small. But even so, when I calculate this, I don't have a piece of this wire with me, but you won't, when you put 10 pounds on it, you won't see anything. Okay. So generally speaking, in Merkey, unless you're dealing with really compliant materials, the amount of this deflection is small. On the other hand, when you start to put together composite columns, as will be in problem set 4, or other structures, then you need to take account of the deformation in order to get the distribution of stress, because they're statically indeterminate. So while the numbers are small in practice, the effects can be significant. In fact, if you don't take account of them, you will not be able to solve the problem. This is something else you've also seen. Torsion. Will principally be concerned with torsion that are either right circular cylinders or hollow circular cylinders. And just like the tensile specimen, we applied an equal opposite force, we have to apply an equal opposite torque to keep it in equilibrium. Then this thing will produce a rotation phi. And phi is TL upon GJ. Okay. This is analogous to what we have here. Delta is FL upon EA. Okay. And so this is like the torsional stiffness. This is the length. This is the torque producing the deformation. This is the force. This is the axial stiffness. G here is the shear modulus. J is the polar moment, sometimes with the polar moment of inertia or the polar area moment. Is it more? Lots of books call this moment of inertia, and that's fine. That's become accepted use. There is actually no mass term in this. That's really an area moment. And again, if you have compliant material, you can get appreciable deflections. With steels or aluminums, you get relatively small. Let's see, I'm not sure if you're able to see this. Okay. All right. Okay, I've got this tube, and I'm going to apply a little torque to this thing here, and you'll be able to see that the thing that's at 12 o'clock will move appreciably. Okay, and so in compliant materials, appreciable. In steel, small, but again, not insignificant, because you're going to need them for statically indeterminate problems. But I started off this introduction by saying sometimes deflection criteria. Deflections are usually so small in steel and aluminum products that deflection is negligible. You don't really have a design criterion for it. Okay, you don't need to worry about it. It hardly moves. That said, we still need it for statically indeterminate metal structures. That's all mechanics and materials. And we're going to start doing bending, which is also mechanics of materials. But let me start off. We're going to use the following sign convention. And that's what you have to use to get things correct in tests on this course. This is a small element of a beam. I'm going to draw it big so we can see the resultants on it. There can also be concentrated loads, but W is a distributed load. So its units would be pounds force per inch, Newton per meter, something like that. And it's positive when it acts down. Okay. That produces a shear force. And the shear force convention we'll use is the standard civil engineering convention, which is dominant in engineering and MECE to this day. And it would be in pounds force or newtons. And it's positive when producing a clockwise rotation. And then there's the bending moment. It could be pounds force per inch will be the standard unit. Whether you put this F in here or not is arbitrary, up to you. I prefer it. And it's positive when you compress the top of the beam. This is a civil engineering convention because predominantly they design floors, okay, and like structures. And what happens is the bending moment compresses the top and the bottom part goes into tension. The loads are down, typically down on things, and this is the bending moment they produce. So this is the natural sign once you pick this W. Okay? And this is the natural thing for civil engineering. That said, this same sign convention, to the best of my knowledge, I've never seen anybody in MECE, practicing MECE, use different sign convention in the years I've been doing consulting. Now there was the book is changing M around. You do that, you're going to be marked wrong with a sign error. I'm teaching this way because this is what you see in practice. Juvenal and Marshak went along with some other academics who thought maybe it'd be better to have the other bending moment. I have no idea why they did that. Okay. But in any event, we're not going to do it. This is what you're going to see in practice. Once you have these, so it's a natural thing. When you think about stepping on a floor or a floor, a light floor, say a plywood floor, so you feel the give. You feel the give go down, okay? And then, and the top would be in compression because the load is down like this. If I have an X coordinate in this direction, then I can look at a little element and I can relate these. I can relate the change in W will be minus dV dx with this sign convention. And And I can relate a change in M. I have M here and M plus dm here. And that, I can relate that to the moment due to V, and I get so those are the right interrelationships between these two resultants. This is an applied load, this is a resultant shear force, a resultant bending moment. These are the correct ones with this sign convention. And let me introduce the flexions then. And again, we'll use the civil engineering sign convention. This always slightly bemused me. This is traditional, it's positive upwards. Okay. You would think if you went with this, you'd make it positive downward, but this is the way it's been done. And once you have this, you have the following differential equations to solve for delta. Some people use lowercase v for the deflection. Because I'm going to use uppercase V for the shear force, I don't want you trying to distinguish between my lowercase handwritten V and this uppercase V, so we use delta. So the second derivative of delta is related to the bending moment M divided by EI. EI is the bending stiffness. E is Young's modulus. I, strictly speaking, is the second area moment. It's a little different from the polar by a factor of 2 typically for cylindrical bodies. When you have this, and you start to solve for deflections and bending, this is a second differential equation you're going to integrate twice. When you integrate, each time you integrate, you get a constant of integration. And so you need a way of valuing. So this needs 2 end conditions. Okay. You may have different M's for different parts of your beam. Every time you switch M, you'll switch this equation. Every time you have one of these equations, you need 2. Some of these end conditions may be matching. You can differentiate this well, you get D3. And you'll get dm dx, or dm dx is V. This is an alternative equation relating the third derivative to the shear force. So there you're going to need, every time you have a different shear force, you're going to need, and have a different equation. Every time, I should have said 1. Whoop. One needs 2 for whatever range it holds over. So if you have different ones, you're going to, each one of them have 2. So this would be 2. Well, you're going to integrate 3 times. And so every time you integrate, you've got a constant integration, you're going to have an end condition. Okay. You could do this one more time. In which case you'll get the fourth. And you get dv dx. One at the top here, dv dx is minus w. And this is going to take 4 end conditions. Now, civil engineers have their own approaches to these things, a little bit different from Mechie, But a Mackey, dominant stress is going to be bending, so you always have to find this out anyway. Okay? There is some body of thought that's a little bit hard to read, sorry. That you should start with this, and then you don't have to worry about getting the bending moment. You're always going to have to get the bending moment. You're going to, in effect, get the bending moment when you come up with these end conditions. That's what you're going to do. On the way to integrate this, you're eventually going to get to this, and then you're going to integrate this twice. I think you're much better off as a practicing ME to go get this M and solve this equation. You want to get good at getting bending moments. Bending stresses are what break things in Mackey for the most part. And so you want to get them, you need the bending moments. You're better off just learning how to do it. Now, this is an alternative approach. If you do it accurately, it will work, okay? But you're better off developing physical understanding of M and integrating it twice. That's what we're going to focus on here, is using this. That's not to say you can't use these others, okay? And so we'll start doing some more of that next lecture. And that some of these problems will be on problem set 4, which I'll post later today. I don't need question. You can just think of what I wrote down here. It's just ground rules for this course. This is what we're going to use. These are the equations we're going to use. This is what you need to use. Okay. And I'll bet you this is the sign convention you use in practice. Any questions?
Dr. Sinclair,
Yes.
on the rightmost page, what was the formula at the very top, the M equation? I didn't get it all the way down. Is it? Yeah. Oh,
Sorry.
thank you.
Yeah, I wrote too far down here and I slid it up too high. My mistake. Yes, W is minus dV dx. I mean, what you do, you let V vary for a small element dx, then the force down would be W dx, and that would be equal to the force up. That would be V minus V plus dV. Okay, these V's cancel, and you get minus dV. Okay? And so dVW equals minus dV dx. This is stuff I'm sure you had some time ago in mechanics of materials. And you can do the same thing here. You have M vary from M plus dm, and you take moments about the center, and you get V times dx upon 2 plus V times dx upon 2 equals dm. You get this. Okay? That's where they come from. But that's these signs here are an outcome of this sign convention. Okay? If you have a different sign convention, you get different signs here. This is the sign convention we're going to use. Any other questions?
That's it. Thank you, sir.
Okay. Yeah, I'm sorry, I wrote too far down the page here. I slid off. My mistake. All right, have a good day.